In this video, we solve problem 15.R.027 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. The problem statement says, evaluate the line integral along the given paths. We have the line integral over c of x squared plus y squared. In part A, the path C is a line segment starting at x equals 0, y equals 0, and ending at x equals 4, or 3, y equals 4. And in part B, C is a different path. It's actually a circle of radius 1 centered at the origin. And we're asked to go 1 revolution counterclockwise around that circle, starting at x equals 1 and y equals 0. And before we get started on these, I just want to remind you of the difference between a line integral of a scalar function or a scalar field and a line integral of a vector function or vector field. In both of these formulas that I have listed here, I'm looking at functions in the plane and fields in the plane. This would be very similar in 3 space, just instead of having an x and y here, I would have an x, a y, and a z. And similarly, if our field were in 3D, f would be a function of x of t, y of t, and z of t right here. Okay, so if you're evaluating the line integral over c of some scalar function of 2 variables, basically you've got way too many variables here. You've got some path. At t equals a, you start here on the path. At t equals b, you end up here on the path. We need to, in order to evaluate this line integral, we need to come up with a parameterization of that path. Often it's given to us, but sometimes, like in these problems, in parts A and B here, the parameterization is not given to us. But we're told what these paths look like, and each path can be associated with a parameterization r of t. If we're in the plane, r of t has components x of t and y of t, and at t equals a, we end up at 1 location, and then as t ranges from a to b, we trace out the path, and at t equals b, we're at the endpoint. So every point on this path can be represented by x of t and y of t. So every location can be written in terms of t. So when I see this line integral over the path of this function, I need 1 variable to tie them all together. Given this parametric representation of the path, or parameterization of the path, we can use the variable t to tie everything together. So this line integral is evaluated by evaluating this regular integral. It's just a function, or the integrand is just a function of t, and we're integrating from t equals a to t equals b. Okay, so let's talk about how we change this over. Instead of saying the line integral over c, we put our bounds here. Wherever we start with t and wherever we end with t, those are our upper and lower bounds. Now this function, this scalar function, or sometimes it's called a scalar field of x and y, it can be written in terms of t. When I'm on this path, x is given by x of t. So this function f can be written in terms of t by replacing x with x of t and replacing y with y of t. So now my function f is written entirely in terms of t, and that's good. We can do that because when we're on this path, that's going to give us the right value of that function. So this is this in terms of t, and then ds is a tiny distance along that path. Now one way that you can remember this, or one way that I remember the formula for ds, is you remember in pre-calculus or college algebra or high school algebra that distance was equal to speed times time. That's exactly what we have right here. This ds, this tiny distance traveled, is the speed, which is the magnitude of the velocity times a tiny time. So you replace ds with this, you replace the integrand with this, and you integrate from t equals a to t equals b. Just 3 steps, and then you evaluate the integral. Now, if you have something that looks like this, or this, or this, these are line integrals of vector fields. And these, we're doing something very similar. Eventually, this is just going to be a function of t. However, we're starting with vector functions. We're starting with a field f. Now, this one doesn't look like a dot product. Those 2 are dot products. But there is a dot product implied in this. So if I want to evaluate one of these, I need to tie everything together with t as well. Now, if our field is in the plane, we integrate from t equals a to t equals b, the same values that gave us that starting point and that ending point. Then we write our field in terms of t by replacing x with x of t and y with y of t. If we were in 3D, we would also replace z with z of t. And then you dot that with r prime. If this is r, remember you take the derivative component by component. And then you'll have a vector in terms of t, another vector in terms of t. You take the dot product and evaluate the integral. Okay, so when I look at this problem, I say to myself, well, which case am I in? Well, x squared plus y squared is a scalar function. So this is what we're doing. There's no dot product in this problem. We just need x squared plus y squared. That's our f of xy. Entirely in terms of t, we need the magnitude of r prime of t, and we need to multiply by dt and then evaluate the integral. Now this time we're not given r of t, so we have to figure out what r of t is by coming up with a parametric representation or parameterization of the path that starts at 0, 0 and goes to x equals 3, y equals 4. Now there are infinitely many ways to do this. I always like to start by sketching my path. It's just a line segment. So that's C. Since we are talking about a path in the plane, we know that r of t will have components x of t and y of t. And then we can come up with a parametric representation of this line segment. Now you've got options here. There are infinitely many ways to do this. One way is to find the equation of this line. We know it goes through the origin. We go up 4 and over 3. So the slope is 4/3. So this is y equals 4/3 x. So if we wanted to, we could let x equal t. And if x equaled t, y would equal 4/3 of t. And that's one possibility. And if x equals t, and x starts at 0 and goes to 3, well then t should go from 0 to 3. So that's one way to represent this. Another way to represent this line segment is to say, let's let x equal 3t and let t go from 0 to 1. If x equals 3t and t goes from 0 to 1, well, you'd say to yourself, well, what does y have to equal? If I replace x with 3t here, that 3 in the denominator times the 3 in the 3t, those will reduce and we'll end up with y equals 4t. So you could use this parametric representation, it would work, or you can use this parametric representation. Either one is fine. This is kind of what we did earlier when we were making these tables where you've got x here and t here. We're saying x increases by 3, so we want t to go from 0 to 3. Meanwhile, x starts at 0 and ends at 3. So it looks like x and t are the same, so x must equal t. So you can do that, or you can do this. This one's a little bit more intuitive, but this method that we talked about in earlier videos, it will work all the time. Now, for whether you choose this one or this one, you're going to get the same answer for the value of the line integral. I'm going to do this one just because the arithmetic is just a little bit easier, but either way, you're going to get the same value. Okay, so we have our line integral over c of x squared plus y squared. And rather than having that verbal description of c, now we have c given by the parameterization x equals 3t, y equals 4t, for t between 0 and 1. So this is my x of t, and this is my y of t. Now remember how we do this. We evaluate from one t value to another. That's our a, and that's our b. So we'll integrate from 0 to 1. And then we need the integrand, x squared plus y squared, in terms of t. And we find that by replacing x with 3t and replacing y with 4t. Got a product there. You're squaring them, so we square each factor separately. So it's 9t squared plus 16t squared, or 25t squared. So that's our integrand in terms of t. And then remember what ds is. You need ds in terms of t as well. ds is the magnitude of r prime times dt. R prime is a vector with components 3 and 4 because those are our derivatives. The magnitude of that vector comes from taking the components, squaring them, and adding them, and taking the square root. 9 plus 16 is 25, and the square root of 25 is 5. So ds is the magnitude of r prime of t times dt, so we just end up with a 5 times dt. So you've replaced your integrand with a function of t, and you replaced your ds with the magnitude of r prime of t dt. Then we just evaluate this integral. I've got 25 times 5 is 125. You can pull that out front. Then we use the power rule, add 1 to the exponent, divide by the new exponent. Oops, we don't need a plus c. It's a definite integral. And we evaluate from t equals 0 to t equals 1. And at t equals 1, we get 125 over 3. T equals 0, we get 0. So this is the value of the line integral in part A. Now, if you chose to use this parameterization instead, your r prime is going to be different and your integrand is going to be different. But when you're done, when you simplify them, you're going to get 125 over 3. So it'll work out. Now, part B is very similar. But now we're going counterclockwise around the unit circle. So now we need the parameterization of this path. And of course, there are infinitely many ways to describe this path, x squared plus y squared equals 1. But whenever I see a circle, I always think of sine and cosine, and especially a unit circle. And I've drawn my arrows pointing this way, going around this way, because we were told that we're going counterclockwise around this circle. And we're starting here at x equals 1, y equals 0. Well, I think we're all familiar with the parameterization of the unit circle. If x is cosine and y is sine, and the angle goes from 0 all the way to 2 pi, we get the whole circle. Now, in trig class, we called that angle theta. This time, we're going to call the angle t. So x will be cosine of t, and y will be sine of t. And as t goes from 0 to 2 pi, we will trace out that circle. So we are evaluating this again. The first thing we need is new bounds. Well, our bounds are the values of t that allow us to trace out that circle. So we start with t equals 0, and we end with t equals 2 pi. And we've got that right there. Now our integrand is x squared plus y squared, but when we're on the unit circle, x squared plus y squared equals 1. So this f of xy simplifies to 1 this time. That's f in terms of t. I know there's no t explicitly written there, but that's what that is. Now, if you're not completely comfortable using this equation, x squared plus y squared equals 1, to replace x squared plus y squared with 1, let me show you how we would find that using these parametric equations of the curve. If I'm trying to write f of xy, which is x squared plus y squared in terms of t, I replace x with whatever parametric equation I have for x over here, and I replace y with whatever parametric equation I have for y over here to describe that path. In this case, x is cosine of t and y is sine of t. And we know if we square those and add them, we get 1. So we get the same thing using the parametric equations as we do when we use the equation of the path that was given to us. Okay, now you also need a ds. Now remember, ds is the magnitude of r prime times dt. Here is r. To find r prime, we take the derivative component by component. The derivative of cosine of t is negative sine of t. The derivative of sine of t is cosine of t. And then if we want the magnitude of that, we take the components, we square them and add them and take the square root. I think we can see we've got sine squared plus cosine squared again. It's going to be a 1. And if you're wondering about that negative, remember negative times a negative is a positive. So the negative goes away when we square it. And we end up with the square root of 1, which is 1. So ds is the magnitude of r prime of t dt, but r prime is just 1. So ds and dt happen to be the same in this example. Okay, so now we just have the integral of 1 with respect to t evaluated from 0 to 2 pi. The antiderivative of 1 is t with respect to t. We evaluate from 0 to 2 pi. We get 2 pi minus 0, which is 2 pi. So that is the value of this line integral over this curve.